So next question. How is it that the medulla of the kidney is more salty than the cortex? How does that difference in concentration that we're talking about, going from not so salty to really salty, actually happen? So there are three things that help us to maintain that. The first two up here are actually interrelated. There's transports of solutes and diffusion of water across the loop of Henle. Remember, the loop of Henle comes down and up, going deep into that medulla. So there's that. And then remember that I've got that vasa recta, that blood vessel that's right next door. How this stuff gets out of here and into here influences how this works. And then finally, you've got the urea recycling, which again plays a part in it being more salty in the medulla than in the cortex. So 1 and 2 are interrelated. So I've got one tube, let's say the loop of Henle, and the loop of Henle has fluid going this way. This is our urine going this way. Yes? And then we have the vasa recta, which is another tube right next door. Except in this case, that's terrible. Hang on. In this case, the fluid inside of that is going in this direction. Do you see how the two directions of fluid movement are opposite? One's coming this way, one's coming this way. We call that a counter current mechanism. And what we mean by that is you have two parallel tubes, 1, 2, and the fluid going through them is going in opposite directions. That's why we call it counter current, because one's going this way, one's going that way, as far as the currents of the flow go. So if you look, okay, here is my loop of Henle, and my urine is going this way and then coming back up this way. Yes? So remember that in my descending loop of Henle, I am losing water, right? I'm losing water. This is the thing that I'm getting rid of, is the water. And as I go, my goal is the concentration that's in here is equal to the concentration that's out here in my interstitial fluid. So if this is 600, I want this inside to be 600. If this is 900, in here, I want it to be 900. If this is 1200, I want it to be 1200 here. As it comes back up, I want it to be 900 here. I want it to be 600 here. I want these to be equal on both sides. So if this is less salt, and this is salty down here, right? That means what's in this tube has to become more salty. So how do I make it more salty? Well, I start taking the water out. And as I take the water out but leave the salt behind, it becomes more salty in this tube. Now, when I come up from this, I want it to be equal, right? Well, now I've got a whole ton of salt in here, but this is impermeable. No water is allowed to exit, right? So how do I make it less salty? I get rid of the salt. So when I start coming up, trying to get everything matchy across like this, I start removing the solutes. I start getting rid of the salts. Even up here with my pumps, because remember, this is pumps. I am having to use energy. I'm getting rid of salts. Yes? See how that works so far, because all we've talked about is the loop of Henle. So, those same rules about being matchy actually work for the blood as well. So here's my blood flow. At 300, my blood's at 300. If I get to the place where it's 600, I want the blood in here to also be 600. If I get to where it's 900, I still want the blood in here to be 900. When I get to 1200, I want this to also be 1200. I want it to be equal as we travel down into the medulla of our kidney. So, how do I do that? Well, if I'm really watery here, what do I need to become salty? How do you make water into salt water? You add salt. So, look who's getting rid of salt. So if I pick that up, I get more salty inside of this blood vessel so that I match. And then I come down here and this guy's also getting rid of solutes. So I pick those up too. And as I'm picking those up, I am getting more salty so that I match by the time I get to here. So this salt that I'm getting rid of here and here doesn't stay there. The blood vessel is picking it up. This basically ensures that this stays at 1200, this stays at 900, this stays at 600, because although I'm getting rid of those things from my loop of Henle, the minute that I get rid of them, this blood vessel is picking it up and carting it off. It doesn't sit there. Now again, if I start coming up this tube, if I start traveling up, I still want to do the whole matchy-matchy thing. Now I've got really highly concentrated salt water in here. How do I dilute it? If you had a cup of salt water, how would you make it less salty? You would add what? Water. Well, look who's getting rid of water. This descending loop of Henle is getting rid of water. So as this blood comes up, it just starts picking up all of this excess water that's getting dropped off. And by doing that, I keep my matchy-matchy numbers. I go from 1200 down here to 900 right here to 600 right here. And I keep absorbing until at the end, I'm almost the same. This is about 310. This is 300. Sorry. This is 300, but I mean, we're almost matchy-matchy. This counter current, because this current's going this way and this current's going this way, actually helps me maintain this concentration gradient going from 300 osmoles per liter to 1200 osmoles per liter, meaning I go from being, there's some salt in there, to really salty. By having the counter current and having one pull and the other pick up immediately, it keeps it balanced, it keeps it in check. That is the counter current mechanism that I'm talking about. Now, urea recycling. Urea is a protein byproduct, a protein metabolism byproduct. It's basically a waste product, but it is capable of acting like salt. It is capable of making that salt gradient that we've been talking about. So urea is normally part of the urine and we're trying to get rid of it, but when it hits my collecting duct, the collecting duct actually spits some of it back out into the medulla. Remember, this is the medulla. And believe it or not, we actually pick it up and we put it back into the tubing to get rid of it, and then the collecting duct dumps it off. That's called urea recycling. We're taking advantage of the fact that urea is a type of salt to basically make sure that our medulla, this medulla that's down here, stays salty enough to do what we need it to do as far as pulling water out and pulling sodium out, or pulling salts, I should say, not just sodium out. So the summary of the three mechanisms. The summary. Sodium and other solutes are actively transported into the interstitial fluid of the medulla, maintaining the high medullary osmolarity. In other words, I'm making it salty. The slow blood flow through the vasa recta ensures that the solutes aren't washed away from the medullary region. Basically, I make sure that I'm keeping everything in balance, 1200 to 1200 to 1200. And then much of the urea returns to the medulla from the collecting duct rather than exiting, helping to maintain the medulla's osmolarity, its saltiness. So those are the three mechanisms. Even though the first two are very closely related, it technically is three separate things that are doing this. The collecting duct spitting out the urea, the loop of Henle first spitting out water and then spitting out salt, and then the vasa recta picking up the salt that's been spit out and then picking up the water that's been spit out. So regulation of urine concentration and volume, the hormonal mechanisms in a nutshell. Let's try that a third time. The hormonal mechanisms in a nutshell. There we go. Okay, so this is our renal corpuscle, right? We've got the glomerulus with the Bowman's capsule surrounding it. If you look at my afferent arteriole, you will notice that I've got this little bundle of cells here. Okay? These are the juxtaglomerular cells. The juxtaglomerular cells. As well, this is part of my distal convoluted tubule. Do you see this set of cells here? They look really, really tightly packed. And they are part of the wall of the distal convoluted tubule. They are also right next to these juxtaglomerular cells. I mean, they're right next door to each other. You can see that right there. These are the macula densa. Together, they make something called the juxtaglomerular apparatus. So, its function is to secrete something called renin, okay? And it plays an important role in autoregulation of the filtrate formation, as well as blood pressure regulation. Remember, we talked about the fact that we have to be able to control that blood pressure inside of our kidney because the glomerulus is a capillary. It's teeny tiny. If you put too much pressure behind it, it'll split. So I've got my juxtaglomerular cells and I've got my macula densa. The juxtaglomerular cells actually monitor blood pressure, whereas the macula densa is actually looking at sodium concentrations in the blood. So what stimulates this to happen? There's either a drop in blood pressure or there's a drop in sodium. What are the two things I'm monitoring? The blood pressure and the sodium, right? So when that happens, when there's a drop in blood pressure or a drop in sodium, those juxtaglomerular cells, those two cells secrete renin. So what am I looking to do? I don't have enough sodium and my blood pressure is too low. What should I do? I need to raise my blood pressure and I need to get more sodium. Those are the two things that are going wrong. Let me fix it. So renin gets released. It goes to the body and takes angiotensinogen that is already floating around. Angiotensinogen is always in your body, but it converts it from angiotensinogen into angiotensin 1. Angiotensin 1 actually has contact with angiotensin converting enzyme. It's a proteolytic enzyme found in the capillaries of various organs. ACE, angiotensin converting enzyme. angiotensin converting enzyme, ACE. This is also something that's normally floating around, but now it's been activated, okay? It converts angiotensin 1 into angiotensin 2. It can also be activated directly in times of drastic drops of sodium. So if sodium just drops off really, really quickly, ACE will just be automatically activated. So what does it do? Why do we want angiotensin 2? Well, one, it's a potent vasoconstrictor that increases peripheral resistance in the blood vessel and thus increases blood pressure. Remember, a drop in blood pressure over here, this drop in blood pressure was one of the reasons why we started all of this, right? This drop in blood pressure. Well, if I take a blood vessel this big with very little pressing on it and I make it this big, that's going to cause that little bit that's in there to press a lot harder. It's going to rise or elevate my blood pressure. Second, it increases thirst and salt appetite. If I give you salt, what's the first thing you're going to ask for? Water. What is the majority of my blood made out of? Water. So if I increase my water intake, technically my blood volume should go up. It increases ADH secretion. Remember our antidiuretic hormone that we were talking about? Well, if I don't have enough blood to make my blood pressure, do I really want to lose fluid in my kidney? No. Because if I'm losing blood volume, then my blood pressure is going to drop. So what do? Well, I make sure the kidney's only taking enough fluid to make the urine and clean. Everything else that could be extra, I take back. It also increases aldosterone secretion. Okay, so let's talk about aldosterone. Aldosterone actually comes from the adrenal cortex. Remember, the adrenal gland is the gland that sits above your kidney. So aldosterone, it targets the distal convoluted tubule and the collecting duct of the nephron. Remember, those are the last two sections of that nephron. It increases the synthesis of sodium transport channels in the walls of the distal convoluted tubule and the collecting duct, leading to increased sodium reabsorption. So I'm pulling sodium out of the urine and putting it back in the body. If I put salt in your mouth, what are you going to want? Water. So if I'm pulling salt out of the urine, the water's going to follow. So what that ultimately means is more water is also getting reabsorbed because I'm moving salt. The water is following that salt back into the body. Now, something else. There was that drop in sodium here, right? That also caused this. I'm bringing sodium back into the body here. So not only am I helping with the blood pressure by basically shifting volumes, I'm also bringing that sodium concentration, hopefully, back into homeostasis. This sodium here that was too low, hopefully I'm helping to increase the amount of sodium down here. Whoops. Whoa. So the result of aldosterone release is we decrease the amount of urine we're producing. If I put salt in your mouth, you're going to ask for water. If I start pulling salt out of the urine, the water's going to follow. Because water and sodium reabsorption. Thus, there's an increase in our blood pressure. And there's an increase in the amount of sodium, the concentration of sodium. What caused this whole thing to happen? A drop in blood pressure and a drop in sodium concentration. This reverses that, which is what we want. Now, if you want a simpler picture of this, this is what's in your book. Renin comes from the kidneys, angiotensinogen from the liver converts it into angiotensin 1, angiotensin converting enzyme converts it into angiotensin 2, which goes to the adrenal cortex, causing it to release aldosterone, which causes sodium channels to be made. Sodium comes in, actively transported from the urine. Okay. So, antidiuretic hormone. For those of you that are nurses already, what's a diuretic? What does it make you do? It makes you pee. So antidiuretic, what do you think it's going to do? It's going to make you not pee. So we have baroreceptors. Baroreceptors are pressure receptors in your body. They monitor your blood pressure. We also have osmoreceptors. Remember, osmo always means water. So they measure the blood's osmolality. How watery is your blood? Now, what causes antidiuretic hormone release? Two things. A drop in blood pressure, and there's too little water in the body. Antidiuretic hormone gets released if you're going through dehydration, for sure. Now, I get a signal, the blood pressure is too low, or there's not enough water in the body. It goes to the posterior pituitary, and says, hey, you need to release antidiuretic hormone. So it releases antidiuretic hormone. Function. It goes to the distal convoluted tubule and the collecting duct and binds to a GPCR, a G protein coupled receptor in the cell's membrane. This activates adenylate cyclase, which causes an increase in cyclic AMP production. That promotes the insertion of aquaporin 2 channels into the apical membrane of the cells. So remember that in our tube, the apical part of our membrane was the membrane that's closest to the urine, because this is the basal membrane that's closest to our blood vessel out here. Okay, so I'm basically inserting water channels near where my urine is on this inner surface here. Okay. Aquaporin 3 and 4 channels are always present in the basal membrane, but without aquaporin 2 channels in the apical membrane, they don't function. Basically, it's like having a locked door in the back of your house. And the front doors, let's say I've got two front doors, they open just fine, but I've locked that back door with the deadbolt and I'm the only one with the key. Well, nobody's going to be going into the back or coming in from the back unless I unlock that door. The aquaporin 2 channels are the back door. And if I open these, then the two front doors will allow things to move from my backyard to my front yard. So, I've got a bigger picture of this in the next slide, so I'll show you that in a second. When aquaporin 2 channels are present, water in the distal convoluted tubule and collecting duct is reabsorbed. I can actually bring this water in and move it over here to this blood vessel. It also makes the resultant urine extremely concentrated because the same amount of waste is being produced and excreted, but I'm putting it in less water. I'm suspending it in less water because I'm taking back. So here is a vesicle. Here's a vesicle inside of my cell, inside of my kidney cell, inside of the walls of my distal convoluted tubule and my collecting duct. These are always around. But until I get the signal from antidiuretic hormone, this stays like this as a little vesicle with the aquaporin 2 channels sitting in it, and it never does anything. But when I do get that signal, in other words, my alpha goes and activates CAMP, the CAMP comes and causes these to insert into my apical membrane. Remember, this is the urine. Okay, this is my filtrate over here. Now I can pull water into the cell, and then I've got the other aquaporin 3 and 4 channels that'll just let this keep going to this side. Now this is what I meant. These aquaporin 3 and 4 channels are always there. They exist. They're present 24/7. But since this isn't here normally, They just kind of sit there, really not moving anything massive because there's nothing massive to move. Whereas when I do insert this into place, now I've got water coming in and it can just go through this channel to go into the blood vessel. Okay, atrial natriuretic hormone. So what's the atria? The atria is the top chamber of the heart, right? So in the right atrium of our heart, we have stretch receptors. They monitor how far the walls of that atria stretch. So pretty much the last two sets of hormones that we've talked about have been, I want to get water back in the body because my blood pressure is too low. This one kind of does the exact opposite. Pretty much, if you overstretch this atria, in other words, you have too much fluid, it takes action. So the atrium, the right atrium stretches because the volume of blood entering it is high. In other words, this is like trying to put an extra large pair of sweatpants on a person who's a XX. Kind of stretches a bit far. So when that happens, the right atrium actually releases atrial natriuretic hormone. What does it do? Remember that ADH that we just made to try and make our cells absorb extra water in the distal convoluted tubule and the collecting duct? Yeah, I kibosh that. I make sure that no more ADH is being produced. When I do that, I end up leaving that fluid inside of the distal convoluted tubule and the collecting duct, making dilute urine. In other words, there's more fluid volume harvested from the blood. It's released via the kidney, meaning my blood pressure starts to go down. That fluid volume, that extra volume that I had that overstretched my atria, I'm getting rid of it. Eventually that stretching stops. When the stretching stops, I stop producing atrial natriuretic hormone.